Thank you for coming. Good morning. The last three lectures were sort of self-contained study of various mechanisms for producing dark matter. But basically, we were after one number, the energy density, and I showed you in the focusing on thermal relics, various ways to get it. Today will be different. I want to talk a little bit about phenomenology. So the final lecture will be disjoint from the mechanisms. Now, we'll just assume there's dark matter, not worry where it came from, and then ask about signals of it beyond the energy density. The very lucky case is that it interacts with ordinary particles. So this would be coupled dark matter. And then as you flow time in various ways, you get different ways you can test it. So if time is going like this, that's direct detection. That'll be Ruderman's lectures. If time is going like this, so direct detection, indirect, collider. So hopefully this will happen because this is the way that we would be able to learn the most about dark matter. Oh no.
One day we'll have a dark matter collider.
It doesn't really matter. Okay. Thank you. Ruderman will talk about direct detection next week. Some of the reviews I mentioned in the first lecture are good places to learn about indirect, like the reviews by Tracy and Mariangela. But today I don't want to talk about this because that'll be easy. Come on. So let's make life hard. This is riding up the mountain on a gondola, so today I want to hike up. So I want to consider the nightmare scenario that dark matter only interacts with us gravitationally and show you that there is still some rich phenomenology in that case. And so dark matter may only couple to the standard model gravitationally. For example, if there's a dark sector, and if we parameterize by epsilon the sort of strength of the non-gravitational interactions, we could contemplate the limit that epsilon goes to 0. If dark matter is related to solving another problem like hierarchy problem or strong CP, that motivates couplings that can lead to some of this. But if dark matter is not related to those problems, then there's not really any a priori reason it needs to interact with us, other than that if it does, that would maybe simplify the cosmology. But beyond that, we can contemplate this. So today I want to talk about various bounds on dark matter that don't rely on it interacting with us. And I told you that although these officially are lectures about dark matter, they're secretly lectures to teach you how to do back-of-the-envelope estimates in particle cosmology to give you some intuition, because that's the first step to doing research on this subject. So in that spirit, today's will be very crude estimates. So anybody who has worked deeply in any of the topics I'm going to talk about today will probably feel nauseous. But I want to kind of show you where the scales of some of the bounds come from and parametrically to give you some intuition for them. So things will be admittedly crude. Okay. So first I want to talk about what is the minimum mass for dark matter. And there's a different answer depending on whether dark matter is a boson or a fermion. So we'll consider both cases separately. And I'm going to begin with bosonic dark matter, which will have a lower bound, and then we'll see that there's a more powerful bound we can place on the mass of fermionic dark matter. So we see evidence for dark matter in gravitationally bound structures like the Milky Way and other galaxies. That fact already constrains the mass because the de Broglie wavelength of dark matter should fit within the objects where we observe it to be. The most powerful bound on the mass can be set using the smallest objects, and the smallest objects where we see evidence for dark matter are what are called dwarf spheroidal galaxies, which are small structures. So for example, around the Milky Way, there are we've observed tens of these dwarf spheroidal galaxies. Okay, so the de Broglie wavelength, lambda chi, must fit in dwarf spheroidal galaxies. So if I draw some dwarf spheroidal, it has a mass and a radius, and then the de Broglie wavelength of dark matter should be smaller, roughly than that radius. Yeah.
Is it correct that we have not observed dark matter in these galaxies?
We infer it from the stellar motion. Yeah, from the motion of stars.
In these small galaxies?
Yeah.
Okay,
Then we can estimate the mass just as we can in the Milky Way. Yeah, so in dwarf spheroidals, there's evidence for dark matter, and then we infer the mass from the motion of the stars. Yeah.
Sorry, but the dark matter halo is usually larger than the standard model halo, right? So when you see like
For the Milky Way, yeah.
in general that's not true.
For dwarf spheroidals, I'm not sure, but I think it's roughly the size of where the stars are, but I'm not exactly sure. But anyway, I'll give you some numbers of what I'm going to use, and this is going to be very crude. Okay. Well, first, let me give you some number for the Milky Way halo, where indeed the halo is bigger. So for the Milky Way, the mass is about 10 to the 12 solar masses. The radius of the halo, which is bigger than where the stars are, is about 100 kpc, kiloparsec. Now, just to give you some very rough numbers for what we expect for the size of the halo for dwarfs, the smallest ones that we've observed have masses of around 10 to the 6 solar mass and radii about 0.1 kpc, very roughly, and that's the halo. Where the mass of, so we normalize the mass of the sun, which is 2 times 10 to the 30 kilogram, or just for fun, in particle physics units, it's 10 to the 57 GeV. Okay. So we can, the de Broglie wavelength, since dark matter is non-relativistic, depends on the velocity. So we need to know the velocity that dark matter particles are moving in this halo, and we can estimate that using the Viral theorem, which for gravitationally bound objects tells us that the average velocity is about, given by the following, where it depends on the mass and the radius and Newton's constant. And if you plug in for, say, these numbers, well, first for the Milky Way, you get 7 times 10 to the minus 4, where C is 1. So this is 200 kilometers per second. So that's for the Milky Way. But we're actually going to be interested in dwarfs. And you're slower because they're smaller. So you get 2 times 10 to the minus 5, which is a few kilometers a second in dwarfs. Okay. Now, so this bound that the radius is larger than de Broglie. So I can write that as Planck's constant over the average momentum. So that's 2 pi, h is 2 pi over m chi average velocity. And then plugging in these parametrics and writing G Newton in terms of m Planck, I get the following expression. And then, right, so we have this. And then I can rewrite this as a bound on the mass. And I get the following 2 pi m Planck over the geometric mean of the halo mass and the halo radius. So that's what I was after, some sort of simple parametric expression. And now if I plug in for the parameters for a dwarf halo, I get about 5 times 10 to minus 22 electron volts. and actually, which is within an order 1 number of the real bound when people do this carefully. So you can get sort of a rough understanding of the scale with this very simple parametrics is sort of the bottom line, even though this is very crude. Models that are near to saturating, yes, people argue about what the actual bound is, looking at, for example, the motion of stars and galaxies and near the center, and get numbers between 10 to the minus 22 and 10 to the minus 21 eV. So there's a bit of a spread. But models that are near to saturating this bound are interesting because they can have observable effects on galaxies, and these models have been called fuzzy dark matter. So I'll give you a very recent reference, although the idea is older than this reference. Or if you read this, you can get a much more precise understanding than this very crude estimate. And I want to emphasize that if the Broglie wavelengths were much larger, then it wouldn't fit, and you wouldn't be able to have that amount of dark matter, roughly. So it's clear that you cannot have have a Broglie wavelength much larger than something you're bound to. Near when they get near each other, then you need to actually read this paper. But it's clear that you couldn't be much larger. I want to emphasize that this bound applies to all dark matter. So if all dark matter is a single particle, it has to satisfy this bound. If you have a subcomponent which makes up, say, less than about 10% of the energy density, this bound wouldn't apply because the other 90% that satisfies the bound could form the dwarfs. So this doesn't tell you that you could still have particles lighter than this that could be interesting to look for. So this bound does not apply to sub-components with omega less than roughly 10% of the total dark matter. Okay. Any questions so far?
Also for fermionic dark matter or only for boson?
This applies to anything, but it's a much more powerful bound that I'm going to now explain for fermions. So bosons are the only thing that can get near this, as we'll see in a second. Okay. So next, fermions. In this case, it's named the Tremaine gun bound after the first to propose it. This is one of the first precise ways that we were able to exclude all of the dark matter being made of neutrinos, which was the question that they were trying to address in the original work. And it's just the fact that fermions have a Fermi degeneracy pressure, which limits the amount you can fit in an object, and that's a much more powerful bound than just this de Broglie wavelength consideration, as we'll now see. So fermion degeneracy pressure sets a minimum halo mass. So let's very crudely work this out. So the halo mass would be given by the mass of the dark matter particle times the number of dark matter particles in the halo, and the number of particles I can write as the volume times the number density. And the number density is given by the integral over the phase space distribution function. And then very roughly, for fermions, you cannot have large occupation number, so F needs to be less than 1, roughly. Only bosons, all in the ground state, can have large occupation. So very roughly, we can say that this should be less than M V D3P, where I'm just using that F is less than 1. And that would just be M chi V times, so since you're non-relativistic, well, yeah, so sorry, I'll put this this will be volume is a capital V, and I'm going to now velocity is a lowercase v. Okay? And now I can write this in terms of halo parameters. So I'm neglecting order 1 numbers, so I'll just write this as radius cubed. And the velocity, so that's the volume. The velocity is still given by the Viral theorem. So I can plug in these two expressions into here, and then I can rewrite this as a bound on the mass. And if I keep track of all the powers, as you can check, I get the following. M Planck to the 3/4, radius of halo to the minus 3/8, mass of halo to the minus 1/8, which has the right units. And if you plug, so you again get the strongest bound from the smallest objects. So you could have applied this to the Milky Way, but you get a stronger bound from the dwarfs. So plugging in these dwarf parameters into this expression, I get about 0.4 keV, which is within a factor, an order 1 factor of the bound when you do things carefully, amazingly. So I'm proud of the fact that I can get things right to a factor of 2 by these very stupid back in the envelope estimates. Yeah, so here again. So I've plugged in 0.1 kpc and 10 to the 6 solar masses. If you want to read a more careful analysis where they actually compute the phase-space distribution and apply it to dwarfs, in a recent reference from the Irvine group is the following. And here they collect the parameters for various dwarfs and apply the analysis dwarf by dwarf and get numbers sort of roughly that size, more like 0.1 eV, 0.1 keV, sorry. So from this, we can conclude, for example, that dark matter is not all composed of active neutrinos, which would violate this. And again, just like this fuzzy bound, this applies to 100% of the dark matter, cannot be a fermion that violates this bound, but it doesn't really apply to subcomponents even up to about 10% of the energy density could be a fermion that violates this bound. You just need to have enough dark matter to form the dwarfs, so does not apply, again, to subcomponents. With omega less than, say, 10% roughly of the dark matter. You can argue about the order 1 number there. Yeah?
Is there any reason you can't have the halo just be larger than the galaxy?
We see the size. Yeah, so from stellar motion, we constrain both the mass and radius of the dwarfs. So these numbers are observed.
But based on mass?
Based on stellar motion, yeah, and then assuming gravity is explaining it, you can track, yeah. Worse. Yeah, I'm forgetting exactly the number. You can plug in as an exercise. Yeah, I remember I did it here, and it was 4 or 5 orders of magnitude worse. I forget. Maybe tens of eV, if 100. Yeah. Was there a question there?
So in order to make it more precise, you need to take into account the fact that the distribution is not known. You actually need a 60 distribution. Like galaxies are not smooth and uniform.
Indeed. So this is very crude. I recommend this reference for where they precisely compute the phase-space distribution. Amusingly, this gets the answer they get within a factor of 4. So indeed, there's an order 1 number here that I recommend looking at that paper. So, and kind of so the neat thing is in both of these cases, the mass bound is just a function of M Planck, the mass of the halo and the radius of the halo. It just ends up as a different power in both cases, and that is all the difference between 10 minus 22 eV and a keV. Okay.
How does this picture change if we think about, maybe the galaxy is not in equilibrium yet? Maybe there's phase space.
Yeah, indeed. So you need to actually compute this, and then for a different model of the halo, you can get different answers, and that can change the bound at the order 1 level. Here I'm just assuming they all have 1 momentum, and that the phase space F is 1. So it gets corrected by an order 1 factor as you vary the modeling. Okay. Any more question? So that's step 1, minimum mass. The next point will be related. There's a requirement that dark matter be cold when the first structure forms. And as I'll now describe, this also allows us to place a constraint on its mass. And models that would saturate this bound that I'm going to now describe are called warm dark matter. Dark matter should not be too warm, is the origin of the bound. Okay, so very crudely, structure formation is like galaxies is due. You have random perturbations of density, and the regions of high density form structure. So structure forms from initial dark matter overdensities. So if I have regions of higher density, this would form a structure here, and maybe I form a structure here and not there. But the dark matter, if it had a thermal origin, if it's a thermal relic, it has some Maxwell-Boltzmann phase space distribution initially, so they're randomly moving. So you can think of each of these particles having some motion. And initially, before it becomes matter-dominated and these things are gravitationally bound and collapse, initially the dark matter is just free. We say free streaming. It's just freely moving as an initial condition before things clump. So I'll call the distance it moves LFS for the length it free streams. Now, the sort of smallest size that we presently constrain these to have, it should be larger than about 0.1. We see things down to scales of about 0.1 megaparsec co-moving. So 0.1 megaparsec in the size of today's universe, which would be a smaller size by the scale factor in the past. So the sort of size of structure. We see things at all different sizes, but that's sort of the smallest that we constrain. So we can define, so there's some physical distance that each particle moves, and then we can define a co-moving free streaming length in terms of how far it moves in today's coordinates. So so I'm going to define a co-moving which I'll label lambda fs, and then the actual physical distance that it moves will be divided by the scale factor at the time it's moving. And what happens is as it free streams, structure is washed out on scales smaller than the distance that each particle can move. So if they all randomly move by a certain amount, then you won't see structures, and you'll remove structures smaller than that amount. So structure is suppressed on scales L less than lambda Fs. I mean, since lambda Fs is co-moving, then that would be the length of the today. And then when you actually do detailed bounds, well, you find that this lambda Fs should be smaller than about 0.1 megaparsec, because as I said, that's the size that we probe the structure down to. In practice, these bounds often come from analyzing things like Lyman alpha first. I'll give you a reference if you want to learn about this more precisely. Okay, but I now want to ask, what does this constraint imply in terms of the dark matter particle physics? So the precise way that we can define this is by an integral of the velocity of each dark matter particle over the scale factor. So dividing by scale factor makes it co-moving. And you want to integrate, well, 2 today, in principle. And you can start the integral at the time where the dark matter kinetically decouples, assuming that it is interacting as part of some, it's interacting with a standard model plasma or a hidden sector plasma if it's a thermal model. So it's at the moment when those interactions decouple that it now streams freely. So we want to compute this. So t is the time of kinetic decoupling. And then, well, there are various particle physics scenarios one can apply this to. So I'm going to just show you one example to give you a taste. I'm going to consider that dark matter kinetically decouples from the plasma before becoming non-relativistic. At time t and r, which is when the temperature crosses the dark matter mass. This would be the case, for example, for the freeze-in or super WIMP scenarios we discussed. It's also the case for gravitinos and sterile neutrinos. So there are a lot of examples of, especially in the FIMP regime, of where it would kinetically decouple while still relativistic. So let's compute. So we want to calculate this. And you can break the integral into 3 parts, from kinetic decoupling to when it turns non-relativistic, from when it turns non-relativistic to equality, and then from equality to now. And if you do this, you find the integral is dominated by, so most of the free streaming occurs.
So you're assuming that it becomes non-relativistic before equality.
Yeah.
Assuming it's not hot there.
Yeah, I'm assuming it's non-relativistic before equality, and the 2 bounds well, sorry, for fermion that's true, but in order, if that's not true, it was definitely not going to be warm. It'll definitely be too hot. So. Yeah, so indeed, T and R is smaller than T equality, I'm assuming. So most of the free streaming occurs between the time where it turns non-relativistic and equality. So therefore, the bound is dominated by this part. You can check the other regimes as an exercise. So I'm just going to do the integral here. The scale. There's more time, but the scale factor scales as a different power of time, and then the integral ends up giving a smaller contribution. Yeah, it depends both on the velocity, which is slower by then, and how a scales with t. So it's not obvious, but okay. So I can write the scale factor as a function of time, as the scale factor at equality times the temperature at equality over T, because T goes as 1 over scale factor. Because during radiation domination, Hubble goes as T squared, and that tracks time, so therefore the scale factor goes as square root of time during radiation domination. And like we said in the first lecture, T equality is about 0.8 electron volt. And the velocity as a function of time starts at the speed of light and then redshifts after it turns non-relativistic. So I can write it like this. If I plug in these scalings into this integral and perform the integral, I find the following: 2c T n r over a n r log of A equality over a n r. And by the way, if you perform the integral between T kinetic decoupling and T non-relativistic, you find the same prefactor but not the log enhancement. So the integral from before is smaller by a log, and the integral from later ends up being smaller by a power law. So this is the dominant time. Okay, now I can write the time that it turns non-relativistic as a function of T equality. And then this lets me write it as a function of the temperature that it turns non-relativistic. So plugging that into here, I get the following: 2c time of equality, temperature of equality, over scale factor at equality, 1 over T temperature returns non-relativistic, log so that is a relatively simple expression at the end. Sorry. So now I'm going to plug in. So A equality is about 3400 to the minus 1. This is about the redshift at equality. Is about 3400. The time at equality is a few 100,000 years. Say 6 times 10 to the 4 years. So plugging in these values and this value, the prefactor, so this term in parentheses is 0.1 megaparsec keV, so you can check. So this is going to be the key number that's going to actually determine the mass scale that matters. So it just comes from these simple powers. So therefore, I can estimate the free streaming length as 0.1 megaparsec, 1 keV over the temperature. It turns non-relativistic, and there's this log. So assuming that the temperature of the photons is on the order of the temperature of the dark matter, then the temperature turns non-relativistic is about the mass of the dark matter. And then the requirement that the free streaming length this has to be smaller than 0.1 megaparsec was about, I told you. So therefore, the mass needs to be larger than about 1 keV for it to free stream by shorter than the amount that would wash out structure beyond what we observe. Yeah. Yeah, then that would change where you start the integral. So here by T kinetic decoupling, I mean when it's after the time after which it's inert. So you only free stream if you're not interacting. So I'm assuming that the self-interacting rate and also the interaction with any plasma is slower than the Hubble expansion at times beyond T kinetic decouple.
Just saying that if you didn't decouple, you still have some diffusive motion. So the integral would not be ddt, it would be some square root of.
Sure.
And then I guess that I could get a boundary stuff interacting dark matter, which would be much less sensitive.
Yeah, indeed. It's not free streaming anymore. Also, now you might have some pressure, yeah, which changes the structure formation, which can be modeled by inserting a pressure. And there can't be too much pressure, or else you would block. So you can suppress structure for a different reason. Instead of free streaming, you can suppress structure because of a dark matter pressure. So I think the analysis is different. So for this analysis, I'm assuming that the dark matter is inert for after the time of kinetic decoupling for simplicity, and that would, I think, need to be treated differently. But it is interesting. Okay. So this applies to thermal relics, whether it freezes out with the standard model or a dark temperature. It applies to freeze-in, which imparts it initially with a Maxwell-Boltzmann phase space distribution and to super WAMP. It applies to oscillations, like sterile neutrinos. This does not apply to models of bosonic dark matter, where the dark matter is all produced at zero momentum, like the axion. And there are also models of dark photon dark matter of that type. So this does not apply to those models. It does not apply.
Because you assume kinetic decoupling?
I assumed that it started moving at the speed of light in this integral. And in these models, you start at rest.
It didn't actually have to be in equilibrium with the bath. It just had to be.
Yeah. So see, in this step, I assumed that the velocity is I assumed there was a moment where it turns non-relativistic, and that it was moving at the speed of light before that moment. That's the only, yeah. But that will be true of all of these models where you begin with a Maxwell-Boltzmann phase-space distribution. Okay, so it does not apply to bosons produced at rest. Example is axion or dark photon, dark matter of models of that type, production from misalignment or production from cosmic strings or production during inflation, which are things I didn't discuss in these lectures but are possible. And just like the minimum mass bounds I described before, this applies to all of the dark matter. It does not apply to subcomponents that are making up less than roughly 10% of the energy density. The reference I gave here actually does an analysis of mixed warm cold, and they find a bound on the order of 10%. So if you have something that's 1%, it can be free streaming by much further, and that's not washing out structure because the remaining 99% can form the structure. Okay. Any more questions about warm? So it turns out that the number keV is right near the Tremaine gun, which is also on the order of a keV, and that's, as far as I can tell, just a parametric accident. So keV is an interesting number for two reasons. It's the smallest mass where you can pack fermions into the structure we see, and it's also the mass below which you would free stream beyond the scales that we observe structure.
So it's not a coincidence?
It is a parametric coincidence. Yeah, it's this is equal to the thing that I wrote before that was a function of the halo mass and halo radius, and this doesn't know about those parameters. So as far as I can see, it's just a parametric accident that you get the keV scale for both of these bounds. If you can explain that accident, that would be amusing. Okay. And I should say models near all of the bounds I've been discussing are very interesting. Fuzzy dark matter is near the lower scalar mass. keV scale mass is interesting both for being warm and because there can be effects from the phase space in these. So it's often the case that there's some bound. Models way past the bound are wildly excluded. Models near the bound are very interesting and can have observable effects, and there are whole groups of people studying all the models near each of the bounds that I'm discussing. So. Okay, so next, an effective. This is the only of the bounds that I'm discussing today where I can, I don't have to work at back of the envelope level. This one's easy to do exactly. So this refers to constraints on new relativistic degrees of freedom beyond the standard model. Relativistic degrees of freedom contribute to the Hubble expansion and are constrained cosmologically. For example, it's constrained by Big Bang nucleosynthesis, and they're constrained by the CMB. So BBN constrains relativistic degrees of freedom when the photon temperature is about an MeV, and then a few orders of magnitude lighter, so below that. And CMB constrains the number of relativistic degrees of freedom when the photon temperature is about 1 eV. In the BBN case, you're comparing the rates of nuclear reactions to Hubble to determine the yield of the reaction network, and then if you change the number of relativistic degrees of freedom, you change the clock, and that changes the rates in a way that would spoil the predictions. And Hubble also enters the CMB power spectrum. So during radiation domination, if you recall, Hubble, we can write like this, where G star I'm now writing as a function of T photon, and you sum over relativistic degrees of freedom. And it goes like each component's temperature to the 4th power. So for n-effective bounds, you can break the theory down into, in the case we're studying bounds on dark matter, we can break things down into sort of 3 sectors that'll be relevant. So there's an electromagnetic sector, which contains the photon and the electron positron. There's a neutrino sector that contains the 3 active neutrinos. And then there's a dark sector, which contains the dark matter, or maybe some mediator like a dark photon, whatever. So in this case, G star E and M. So we have 7/8 times 4 for the electrons, 2 for the left-handed electron, 2 for the right-handed electron, plus 2 for the photon. For the neutrinos, I have 7/8 times 2 times 3 for the 3 flavors. And then here I have some number of dark states in general. And then at different temperatures, these sectors may or may not be in kinetic equilibrium, so you need to track that. So the neutrino is in equilibrium with these above an MeV, and then below an MeV, it drops out of equilibrium. And in general, you could also contemplate models where the dark sector is or is not in equilibrium with either the electromagnetic or neutrino components. You can sort of, this is various possibilities, and you can just plug in a mass spectrum here, determine when these are or are not in equilibrium, then you can calculate G star as a function of temperature, and you can compare it to bounds on n-effective at these temperatures. That's the sort of algorithm. So the convention in this literature is to count the dark states as if normalized to the energy density of neutrinos. So n-effective would be 3 in the standard model, and then delta n-effective would be some change to that. So this is defined to be the dark energy density over the energy density of a single neutrino. So G star d Td to the 4th over 7/8 times 2 times t nu to the 4th. I can write that as 4/7 G star d Td over t nu to the 4th. So let me tell you the bounds. So from BBN, I just looked at a very recent reference, and they get a bound at, so these are 2 sigma. of about 0.4. And this is, just to give you the reference, this is from last month, actually. The CMB bound is actually similar. So CMB only, so if I take the bound from Planck, and if I use CMB only, then it's 0.6. They also do various combinations with other things like BAO or local measurements. But then if you want to combine with local measurements, you have to worry about the Hubble tension. So here I'm just taking the Planck only bound for simplicity. So this is Planck. Yeah, this is as precise as CMB is a big change over the last few years. When I was a student, this was worse by a factor of 2 or 3 than Planck, but they claim to have reduced the uncertainties both on the determinations and on some of the reaction rates, and now the claim is that BBN is as precise, roughly, as the CMB for ineffective. So that's an exciting development over the last few years.
But you can have particles that show up in one and not the other, right?
Yeah, indeed. So that's why. So here you want to compute N effective when the photon temperature is 1 MeV. Here you want to compute N effective when the photon temperature is 1 eV. Those are different. T nu is different in both cases. So in general, for a model, you need to check both bounds, and then it depends on the model which one is more important. Yeah.
So you wrote an electromagnetic spectrum, but it's pretty different if you can only inject photon or you can inject both photons and electrons. Right, so
Oh, here I'm not injecting.
not injecting, but I'm just saying for the simple
So if photons and electrons are in kinetic equilibrium with each other, and if the dark matter is in equilibrium with them, it's in equilibrium with both.
I mean, but then there's the usual, the case of a hidden photon. So I have dark matter that is kinetically mixed. So
Yeah, indeed. So if you have
from dark matter,
if you have kinetic mixing, then that can enforce kinetic equilibrium in this leg here.
but then it really depends on how efficient they are in producing hidden photons that are then converted to regular photons, not only the kinetic equilibrium. Right? Because then
You need to have a model for the energy abundance. I don't know if you're saying you want to populate it from the standard model or not. But what? Yeah. So you do also, when you compute this G star D, you need to have a model that this depends on the energy density. So indeed, if you say kinetic mixing, then that implies some contribution to the energy density. But yeah, that's in this parameter.
yeah, I'm just saying that at some point, I'm now confused about the physics, but at some point you start being sensitive to QCD space condition and get an effective constraint to go all the way up to 200 GeV.
I don't know. Maybe we can talk after. I'm not sure. But here, BBN is sensitive to G star at MeV. CMB is sensitive at EV. Now you do have to. Interesting things can happen. Like you can change in some models. You can change the relative temperatures of these sectors depending on which of these legs are in equilibrium. But maybe we can talk more after. I'm not sure exactly what you're saying. Okay, and I also just want to mention that the CMB is somewhere where there's still a lot of reach. So CMB stage 4, which is the proposed next step, and they claim at the 2 sigma level that they would be able to set bounds as powerful as 0.05, so a factor of 10 better than the current bound. And I'll just give you a CMB stage 4 reference here.
Did stage 3 happen?
Yeah, that's Planck.
Number is stage 3?
Yeah, Planck. Stage 2 is WMAP, stage 1 is Kolbe-Fyrens.
No, stage 3 is Simon's observatory.
Oh, really?
I thought Simon's is like stage 4.
Yeah, I thought that was part of 4, but well, anyway, CMB stage 4 in this reference, 0.05. Planck is this, yeah.
If the next time the number improves, is it
I thought that Simon's observatory was part of this, but anyway, Simon's observatory does have some sensitivity comparable to that, I think. I don't know the exact number. Okay. So you do need to keep track of neutrino temperature, so let me just review that. So weak interactions are in equilibrium until they decouple. So weak interactions, let's just say decouple at about an MeV. So therefore, T nu equals T gamma when T gamma is greater than an MeV. So for the BBN, at the start of BBN, the temperatures are the same. So then you can plug in T gamma here. But they're different by the time the CMB forms, because what happens is that the neutrinos become colder than the photons after E plus E minus annihilation deposits energy into the photons after this decoupling moment. So soon after neutrinos decouple, the electron positrons annihilate away, the photons get hotter. You can compute the relative temperature using exactly the same method I described last lecture for computing the relative dark and photon temperatures. Just call the neutrinos the dark sector and plug into the formulas from before. So if you remember, we had this entropy ratio, which parameterizes the initial condition. We had this. And this, so in this case, the initial condition is that they start at the same temperature. And in this case, neutrinos are lighter than the temperature that we're evaluating it at. So if in that case, it just becomes the ratio of G star in the electromagnetic sector before and after decoupling. Where here T is some temperature below the E plus E minus annihilation. So initially, the electromagnetic sector has both electron and photon. After E plus E minus decouple or annihilate, then you just have the photon. And you get 11/4 to the 1/3, which is about 1.4. So to summarize, the neutrino temperature, when you're normalizing to N effective, is given by the photon temperature for T photon above an MeV, and it's given by 4/11 to the 1/3 photon temperature when the photon temperature is less than the electron mass. Okay. So I now want to apply this technology to a couple examples to see what these bounds actually imply qualitatively for the dark sector. So first example, let's consider a dark sector with T dark equals T photon as a simple choice. And let's suppose that the masses in the dark sector are less than an MeV, so that they're relativistic during BBN. Then we can impose the N effective bound at BBN on this sector. So let's see what BBN implies. So I have 4/7 G star dark, T dark over T nu to the 4th. But then these are equal by this assumption. So this is just 4/7 G star dark. This should be less than 0.4 at 2 sigma by this bound. Therefore, G star dark is less than about 0.7, which is less than 1. So any number of states that have the photon temperature and will be excluded, if they're lighter than MeV, are excluded by the BBN constraint on effective. So dark sector with masses below an MeV must have a colder temperature than the photons to satisfy this bound. And that can only be true if it's kinetically decoupled. So we get a very powerful conclusion that any states below an MeV must be kinetically decoupled from the photons when photons have an MeV temperature. at t equals 1 MeV. So, well, for my next example, let's ask how much colder should the sector be to evade these bounds? So let's consider an example dark sector. Let's take a dark sector, I don't know, let's say a Dirac fermion and a dark photon, and I'll throw in a dark Higgs to give the dark photon a mass. So I'm assuming it's a massive dark photon. And let's assume that all of these states have masses far below an MeV. Well, well, from this example here, we see that these states cannot have the photon temperature at an MeV. They must be colder. So now I just want to ask how much colder must they be? So here we have G dark is 7/8 times 4 for the fermion, plus 3 for the massive dark photon, plus 1 for the Higgs. Delta N effective is 4/7. Well, let me like that. Okay. T dark over T nu to the 4th equals 4/7 times 15 halves. And I'll take the neutrinos to have the photon temperature. And this must be less than 0.4. And then if I solve for this ratio, I find that T dark over T photon should be smaller than about 0.6. So just being order 1 colder is actually enough to let you throw in a whole sector of states. And why is that? It's because the contribution to the energy density goes as the temperature to the 4th power. So even an order 1 amount colder is a very big deal in terms of energy density. So I couldn't even have a single state at the photon temperature, but here I've thrown in a whole family of states with the temperature slightly colder. And it's actually easy to generate order 1 hierarchies like this. If you remember from last lecture, we looked at the case where the dark sector is in kinetic equilibrium with the standard model above the weak scale and then decouples above the weak scale, and then the standard model, because of goes through all the G star depletion, and that makes the dark sector colder by an order 1 amount, and that's enough to satisfy this bound. So for example, if the dark sector starts with T dark equals T gamma and decouples kinetically from the standard model at T0 greater than M top, then we worked out last lecture that T dark over T gamma is G star standard model T0 over G star standard model T. Sorry, I want to ask what the ratio is at an MEV. Minus 1/3. So this was an example that we did last time. It's 106.75 over 10.6 to the minus 1/3, and that's about 0.5, which is smaller than 0.6 by a little bit. So this is BBN safe. So to summarize, if the dark sector has the photon temperature at an MEV, then even a single state's excluded, but a group of states can be consistent with an order 1 bound and an effective with an order 1 colder temperature. And an order 1 colder temperature is dynamically generated even if you start at the same temperature, as long as you decouple before the standard model states decouple. One more example, just to show you from the perspective of the CMB, dark physics. Well, so far I've only considered examples where the contribution to N effective is additive. So we looked at N effective at BBN, and we had new states, and that added to Hubble expansion. But from the point of view of the CMB at an EV, dark states can actually either increase or decrease N effective because they can change the relative photon neutrino temperature. So So I'll highlight that with example 3. So let's consider a dark sector kinetically coupled to the electromagnetic states. And I'm going to assume that the dark sector states are heavier than an electron volt, so that they do not contribute directly to N effective when the CMB forms. Well, let's write it like that. Let's take them to be lighter than an MeV. So in this scenario, they, since they're coupled to the electron and photon, and then they decouple before the CMB forms, it means the electromagnetic sector goes through an even bigger G star transition than in the standard model, where only E plus E minus decouple. Now both E plus E minus and the dark states decouple, and that heats up the photons even more. From the point of view of the CMB, that means the neutrinos are colder. So this model is actually cooling neutrinos. Let's calculate by how much. So T gamma over T nu is given by the G star transition of the electromagnetic sector. So we're going to evaluate this at the, say, temperature where neutrinos decouple. But now, so before this was just the standard model, but now I need to add the dark states. So I have the following, which is becomes the following. So now, N effective, so we have 3 neutrinos. The neutrinos are now colder than they would be in the standard model by the following amount. So this is now, oops, that's G dark. So this is now less than 3. So from the perspective of the CMB, what we've just learned is that dark matter can cool neutrinos, and you can actually observe an N effective below 3. And then the order of magnitude improvement in N effective sensitivity of CMB stage 4 is very interesting in the context of models like this, because then you're going after smaller G darks than you would be presently sensitive to with BBN or CMB N effectives. You could also contemplate models where the dark matter only couples to neutrinos, and then it would heat the neutrinos relative to photons. So you could have either effect depending on what is kinetically coupled to what.
Is it actually taking energy out of the neutrinos? Is this heating the photons?
It's heating the photons, but from the perspective of the CMB, you've cooled the neutrinos. You haven't touched the neutrinos, but yeah.
So if you couple democratically to electromagnetic sector and neutrino sector, you can just get rid of the CMB constraint?
Yeah, indeed. So you can cancel CMB constraint by both cooling neutrinos and adding. Or you could consider something only coupled to, like you can consider this model where you're only coupled electromagnetically, and then I could add some other purely inert states and cancel the effect. So from the point of view of this CMB, there's a flat direction in N effective, but for BBN everything is additive. So BBN closes that flat direction, and then by combining BBN and CMB, there's no way around.
Yeah, but in the mass range between BBN and CMB, if I have something that decouples after BBN.
There is one trick. If you enter equilibrium after BBN, then BBN doesn't see it, and then there's a flat direction from CMB. There's papers like, for example, by Asher Berlin that have exploited this trick, but at least up to that. But yeah, indeed, there is a flat direction from the point of view of CMB. Typically, everything adds for BBN. So if you are in equilibrium, if you are populated at BBN, then there's no way around that. Yeah.
Two questions. What's the lower bound on N effective?
It's on the order of, okay, for numbers I showed before, they're approximately symmetric. So take 3, so what I said, 0.4 or 0.6, so it's like 2.5, whatever.
And you can't do the same check for BBN between like 3 MeV and 1 MeV, like after neutrino decoupling and before you plus the annihilation?
If you decouple before neutrinos decouple, then you don't affect this. Is that what you're saying?
Well, neutrinos decouple around 3 MeV and BBN.
Around an MeV.
There's probably a few MeV to play with. You can do the same thing for BBN.
So you want to exploit that the neutrinos decouple only a little bit before E plus E minus. Yeah. So indeed, if If things are happening right around an MEV, then these sort of simple estimates I'm doing don't apply, and you need to really model it. So here I'm sort of always assuming my states are well separated from an MEV. So I think when you're right around there, things are interesting.
And also for the neutrino decoupling, the E plus minus annihilation to nu, I believe there's a coincidence there too. I mean, one is that this interaction rate compared to Hubble, and that gives us this scale.
Mm-hmm.
On the other
Indeed.
hand, it's also like the scale where electron goes to non-relativistic.
Indeed, there's actually three coincidences. There's three different numbers. There's the temperature where weak interactions decouple. There's the electron mass, and there's the neutron-proton mass splitting. These are all about an MEV. That's all important cosmologically, and it's a parametric coincidence.
Yeah, I mean, my point is that either one means for these two, the neutrino would decouple. Right? Either the electron becomes non-relativistic, there's no abundance of the electron, or the weak interaction rate drops below Hubble. I mean, either way, the neutrino would decouple.
Sorry? The neutrino decouples when the weak interactions decouple.
Right. But suppose that electron is heavier, then it would also it would actually decouple earlier.
Sure.
Right. So either.
And then neutrinos wouldn't be colder. So neutrinos are colder because so the ordering is important.
Right.
And the weak interactions do decouple before
Yeah.
the E plus E minus are gone.
Yeah.
But did you have another question on that?
Oh, sorry. Yeah.
Okay. So any more questions on ineffective?
Why was EV the lower bound here for the top?
Oh, I just wanted to decouple before an EV. If it's relativistic still, then it's not affecting it. So you cool the neutrinos if you decouple after neutrinos decouple, but before the temperature you're measuring. Otherwise I would have to add it here, and then there wouldn't. You could consider that case too. But
by EV you mean CMD a little before, right?
yeah, so you could contemplate that it's still relativistic. So here I'm just taking it to not contribute when the CMB forms it. Yeah, so otherwise we should add this in general. Okay.
Okay, so this n effective lower than 3, so that will even increase the Hubble. So how
Yes.
does that,
And indeed, and if you combine with local measurements at face value with Planck, you can get a more powerful bound on ineffective than the number I showed before for that reason. Personally, I would maybe want to wait until tension is resolved before taking too seriously such combinations implication for models like this, since the resolution would affect the bounds potentially.
Very quick comment. Actually, if you only look at Planck to fit against the Lambda plus the infective, Planck data slightly prefers smaller infective. It's very tiny, not
Yep,
significant.
Planck slightly prefers below, but the tension, if you combine,
If you combine shoes, then it drags it out.
exactly, yeah, that's correct, I agree. Yeah, and the number I showed before was from Planck only. And you can also contemplate Planck plus BEO, but I was showing Planck only. Okay, so last one is quick. How much time do I have?
Say 15 minutes?
We started 5 minutes late.
Oh, that's true. Which one?
The last one is quick because I'm back in Josh units for the next part. So everything I've discussed today involved bounds that don't involve interactions. So it just involved fitting things and energetics. And by my rules today, I don't want to consider dark matter coupled to us, but you can consider dark matter scattering with itself, and that can be interesting. So dark matter may scatter against itself through non-gravitational interactions. This is generically the case in a dark sector. Like if dark matter is charged into a dark photon, then the dark photon mediates a force such that dark matter can scatter against itself. Self-interactions are constrained. For example, cluster mergers constrain dark matter self interactions. So here I'll give a reference where they study an ensemble of cluster mergers and then derive a bound on the dark matter self interacting cross section from modeling these cluster mergers. So the most famous system of is the bullet cluster, although there is, well, now on tens of systems studied in this work, but you've all probably seen the image of the bullet cluster, so I'm going to now draw you a very fancy picture. So there's sort of two clusters that you see, clusters of galaxies whose location you infer from gravitational lensing, and then there's gas sort of in the middle. So the mass you infer from lensing of objects that are behind the cluster. Most of the mass in clusters is not actually in the galaxies, it's in the gas of the cluster, which has a high enough temperature that it's emitting in X-ray. So the gas you see from X-ray telescopes. So famously, images like this are evidence for dark matter and maybe evidence against things like modified gravity, because you see a separation between the ordinary matter and the mass. But also, the interpretation is that these two clusters have already merged, and then during the merger, the gas is disturbed and sort of stripped out, and you can see shock waves if you actually look at the image. I can't. But the dark matter seems to have passed through relatively unperturbed because you still just have these two big balls. So the gas is interacting, the dark matter is not interacting as much as the gas. And therefore, by actually modeling this, you can infer roughly the dark matter interaction should be more rare than the ordinary matter interaction. And more precisely, by modeling it, you can extract a bound on the dark matter self interacting rate. And I'm going to now give you a back-of-the-envelope estimate of what the bound should be.
They're moving outwards, right? They already collided.
They've collided. Yeah. Well, I'm not sure if they're still going outwards or bound, but anyway, they've collided. So a very rough way to estimate the bound is, so during, yes, this is before, you should imagine that we have these two clusters that move towards each other, then they collided. You know, now they're, like you say, they're post-collision. So a very rough bound is that a dark matter particle in this cluster should pass through this cluster and not scatter. So the dark matter mean free path is longer than the cluster size. That's a very rough criterion that would preserve the cluster through the collision. If the mean free path were much shorter than the cluster size, then as dark matter particle passed through, it would be bouncing around, and then you would strip it out, just like in the gas. So here's my cluster, which has some characteristic size. And I should say, I didn't give you any number, but the sort of size of these is about 250 kpc, kiloparsec. So here's my dark matter particle from the other cluster falling in. And it has some mean free path that I'll call LSI for L self interaction. So we want to require that the mean free path is larger than the cluster size, which is about 250 kiloparsec, which is about 10 to the 24 centimeter. So the mean free path is just 1 over the density of the halo. times the self-interacting cross-section. Now, we don't know the number density because we don't know the mass. We know the energy density, so it's useful to rewrite it. So the number density is the energy density, which we infer from the lensing, over the mass. So the energy density is known. So I can rewrite this as rho cluster, which is known, times sigma over m. So it's for this reason that bounds are presented on sigma over m. It's because the rate goes like number density times sigma, and number density goes as 1 over m. Okay. So the energy density of the cluster we measure to be about 6 times 10 to the 4 times the critical density. You can look up the critical density in gram per centimeter cube, and you get, and we multiply by 10 to the 4, you get 10 to the minus 24 gram per centimeter cube. So that's a good choice of units if you compare these numbers. So therefore, sigma self-interacting over m is greater than cluster energy density over length is about a centimeter squared per gram. And this, in sort of particle physics units, ends up being 60 MeV. It's roughly the scale. Okay? Yeah. Oh, yeah. Thank you. Okay. But yeah, so that was my goal, was to be able, and indeed, if you look, when they do a careful analysis, they get a bound of that order. They get point something, 0.4 or whatever, centimeter squared per gram. But this kind of gives you a sense of where that number is coming from. So it really just depends on the density and length scale, yeah.
So what makes their analysis more careful? Is it just that they actually take into account that they...
Yeah, they have more equations than that.
Okay. What is it like? Do they use halo profiles?
Yeah,
Okay.
yeah, they map the profile, of course.
Your mean free path is, right, that's like hand waving.
Yeah, this is very, just saying that the mean free path should be bigger than the size is a back of the envelope estimate. So really you want to ask, would the shape be consistent with the measurement of the shape given some model of the density? Yeah, then you can argue about how well modeled are these cluster mergers, and that's a controversial point. Which,
When you have a picture of it on the after the merger, you need to guess how it looks like before.
indeed, one of the experts on this, who I won't name, told me that you should not trust any bounds on the self-interacting at more precisely than the factor of 10 level. And indeed, in that case, some have already achieved it, but I don't want to demean people working on this. I think it's interesting, and you can do precise things. And you can also, here I've used cluster mergers, you can also get bounds from halo shape, which can actually be competitive. There's a lot of very rich phenomenology involving self-interactions, and also interesting to study them on dwarf scales. Some people think there's evidence, things like core versus cost problem can be addressed by models that are close to saturating this. So there's a lot of interesting stuff to do, but I just want to give you a very back of the envelope way of understanding which models are widely excluded. So the last, yeah. Oh no, let's see. I agree with you, yes. Thank you. That does matter? Okay. Should be this.
You need a dimension -3 something.
Thank you. Thank you. Okay. You should make sure that 10 to the minus 24 gets multiplied by 10 to the 24, not divided by. Yeah. Okay. Thank you. So we can compare this to, say, a WIMP. So for a WIMP, we can estimate the self-interacting rate might be, for example, comparable to the annihilation rate. Which we estimated before should be about 1 over T equality on Planck. This is the WIMP miracle. Or 1 over 20 TeV squared. 1 over 20 TeV squared is a small number compared to 60 MeV. So here, the self-interacting rate would be about 10 to the minus 15 if we took the mass to be an ME, to be a TeV. So WIMPs are not going to disturb the bullet cluster. Okay, an example where you can have observable self-interactions is when the annihilations are forbidden, which was one of the things we discussed in the second lecture. Right, so to remind you here, you're annihilating to something heavier. So for example, a dark photon that's heavier than the dark matter. And now the annihilation rate is exponentially suppressed by the Boltzmann distribution. And then after the exponential suppression, this should be 1 over T equality on Planck. But in this model, the self-interactions are unsuppressed. There's no Boltzmann suppression for the self-interaction. So this we can estimate as follows. So in this model, you have an exponential hierarchy between the thermal average of the annihilation and the self-interaction, and that allows for this to be much bigger and can make up for this factor. And just to show you sort of what scales would work, so sigma over m would be centimeters squared per gram. For example, if I took the mass to be 10 MeV and alpha dark to be about that size, and then you can sort of rescale to choose other values. So these parameters work. You can just choose the correct value of the exponential to set this equal to there, and then you could have self-interactions that are large. SIMPs would also be compatible with parameter choices of like this and getting the right relic density. So large self-interacting rate is not a prediction of a vanilla WIMP model, but it can be compatible with other thermal relics where the mass scale can be smaller and the interaction rate can be larger. So large self-interaction is compatible with forbidden and SIMPs, for example. And models that sort of saturate this bound are interesting and can have observable effects on structures that people are actively looking for. Okay, so that's a good place to end. So again, oh yeah, question?
One last question about this. Where would you enter the fact or the consideration of whether another force is long range?
It's a very good question. Yeah, so I've sort of implicitly been assuming in these estimates sort of a contact interaction, and that would have been the case in this model. In cases with a long-range force, like if the mediator is much lighter than the dark matter mass, then the cross-section that matters can get enhanced at low velocity, so it can become velocity dependent. And that's actually very interesting because then different scaled objects have different velocities. Velocities are larger in clusters and smaller in say, dwarfs. So you can actually change the relative size of self-interactions among different objects in models with a long-range force. And that can help with addressing things like core versus cusp, where you want to have a bigger effect on things with smaller velocity without disturbing clusters. So the relative weight of, say, the cluster bound versus the size of the effect you can get in smaller objects does depend on that. Even with a contact interaction, you can have interesting sized self-interactions that you can look for, and then a long-range force can make it even more interesting. Any more questions on self-interactions? Yeah, so again, officially, these lectures were about to teach you about dark matter, but really, I hope to give you some intuition and some sense of how to do back-of-the-envelope estimates, because if you're going to do research on this, you need to kind of anticipate the answer sometimes before doing detailed numerical work. So I hope to have instilled some of those methods and intuition. Thank you.